Everybody, hello. As Dr. Alex said, today I'll be presenting some of the work we've been conducting at Clemson University on applying self-healing agents into 3D printed concrete, in a subsection of work that we've kind of titled for a presentation, exploring the application of self-healing capabilities and 3D concrete printing and evaluating its effectiveness. If you're not aware of self-healing, there's two main mechanisms in concrete. You have your autogenous self-healing. That's going to come from rehydration of unhydrated cement paste after cracking occurs. That's generally on the smaller scale, looking at microns of self-healing, but is important to recognize for general structures. Secondarily, we have our autonomous self-healing. That's going to come from the addition of a self-healing agent, which will allow for a much more significant magnitude of self-healing. And self-healing agents work pretty simply. It's not the most complex methodology, but it works relatively well, where you're just going to add your self-healing agents into your mixture, disperse it evenly throughout, and eventually, when a concrete cracks, it'll form along a pathway, and you'll rupture your self-healing agents along that pathway. As moisture ingresses into that system, what you'll see is that crack will begin to heal as precipitates form. Typically for bacterial and most other self-healing agents, it's going to be a calcium carbonate forming, but there are some other precipitates as well. And the ultimate goal is that hopefully, when further cracks form, you're just going to be repeating this cycle where additional self-healing agents rupture, they precipitate more calcium carbonate, and you're able to heal multiple cracks again and again. Where things get interesting is when we start to look at structures that aren't cast concrete. 3D printed concrete differs a lot structurally from cast concrete, as well as microstructurally. First and foremost, you're going to have a significantly higher binder content. You're going to have a coarser aggregate, and you're going to have an anisotropic structural behavior. All this means is that you're going to have a larger magnitude of shrinkage, which is going to amplify all of your cracking issues. Secondarily, we have our interlayer areas in our 3D printed concrete. Those interlayer areas typically are much more significantly paste rich, meaning that we have potential for a region of lower self-healing agent concentration. This area, and it's something that we're trying to prove. Additionally, in these interlayer areas, there's generally a higher air content. And using these general ideas, we started to come up with a hypothesis. In this hypothesis, we postulated that compared to conventional cast concrete, the effectiveness of self-healing agents in 3D printed concrete is going to be less effective at healing concretes. And we are kind of building that around the idea that we believe that the reduction in effectiveness is going to be influenced by the uneven distribution of self-healing agent in 3D printed concrete. Essentially, we believe that there may be regions where there is not enough self-healing agent to fully heal our cracks. Now, to test this hypothesis, we did a little bit of due diligence on the back end. We've done some testing with 3D printed concrete before, and we have our baseline control mixture, which includes a 10% addition of metakaolin, as well as a sand to cementitious material of 0.1427 and a water cement ratio of 0.35. We also include a high range water reducer and a set retarder just to extend our open window. And then we modified that mixture portion using a 2 and 4% addition of our bacterial-based self-healing agent, which we received from basilisk. And from that, we did some basic material properties just to give it a little more additional background. As you can see, we have our particle size distributions on our left side, where we have our sand and self-healing agent of comparable particle size distributions, with our self-healing agent being slightly smaller, and then we have our type 1L and our metakaolin as our cementitious materials, even finer than that, forming our paste. We've also included our composition from XRF of our type 1L cement and our metakaolin. From there, we did some basic background testing just to do our due diligence in our 3D printed concrete basic performance. We did 3 rheological measures for 3D printed concrete and 1 mechanical test. For rheological performance, we first and foremost started with testing using the flow table, where we did a height retention test, which is pretty simply molding your sample, and then before dropping the table, you demold the flow table, and you measure the change in height caused by self-weight. Typically, you want to see approximately an 80% retention. We're around that throughout. And then for the flow table test, when you're actually agitating the sample, you want to, typically in literature, we see in excess of 50% being acceptable. Again, we're ahead of that. We're up to 75%. And importantly, All of our samples were grouped together, indicating that we're having comparable rheological performance. We then also did testing with IACAR plus rheometer, just to gather some information on our yield stress and plastic viscosity. Our yield stress is on the lower end of what you'll see in literature, but it is still in the range acceptable for 3D printing from what we saw. And then our plastic viscosity is on a little bit on the higher end. But importantly, what we're seeing is that with the inclusion of self-healing agent, as it is comparable to the particle size distribution of a sand, we're starting to see an increase in our yield stress and a decrease in our plastic viscosity. Lastly, from compressive strength testing, just to get some basic understanding of our mechanical performance, what we found was that we saw a slight decrease in compressive strength at 28 days with the inclusion of the self-healing agent, about 10% going at 28 days with the addition of 4% self-healing agent, going from about 6,750 psi to about 6,000 psi. After doing all this due diligence, we then kind of came up with a plan of attack for our hypothesis. First and foremost, let's start with how are we going to actually generate our cracks. And to do that, there's a lot of work that's been done with mechanical testing to essentially sub-ultimate load fracturing. However, we wanted to generate these cracks naturally, and we did a modification of the shrinkage ring test, where we had to decrease our height and increase our width to make it castable, as well as make slight modifications to exposure conditions, as we didn't want to disturb the sample in its fresh state. Instead of moving it into an environmental chamber at 23C and 50% relative humidity, it was kept in lab conditions and covered with plastic, slightly changing the drying behavior, but as we'll discuss a little bit more, still allowing for the test to occur. Importantly, today we'll just be highlighting our test results for the shrinkage ring testing. We're still working out some of the kinks with our cast 3D printed concrete samples, but we'll get to those in the future. After our samples were cast, cracked, we then transferred them from that 50% relative humidity condition to a 23C 98% humidity condition to allow for self-healing. And after that self-healing, while continuing with that self-healing, we continued two different test methods. We did an optical measurement of our crack widths. That was pretty simple, using a high-definition camera to get a precise photo of our samples, able to get a pixel size of approximately 67 microns, and then using grayscale, converting that picture into grayscale, and using image analysis to calculate the crack widths across the sample using scan lines to create an average value. The second method is the one that we generated, which we are calling the water transmission test. There's been a good bit of work in self-healing looking at water transmission as a method for analysis, as you're not always going to see the full magnitude of self-healing visually. In this test, quite simply, what we did is we placed our shrinkage ring sample on an impermeable surface. We centered that, and we fill it with water. We keep it at a constant water head, and we allow that water to transmit through our crack. It'll go down into the funnel, and it'll collect in a bucket on a scale, and we'll measure the weight change through time to calculate our flow rate. Pretty simple, relatively easy, but it gives us some pretty reliable results. Now, we created two test methods, and there are a lot of questions that go behind that, because how do you know those work? And from that, we created three general questions, and then we had a lot of smaller ones that we collected on the way, but really weren't as meaningful, and we're able to push away pretty quick. Our first question was, does this test matter? Does the modified shrinkage ring test results differ from the conventional ring test? Two, what is the magnitude of crack closure after removal from the test setup? Are we just going to close our cracks because of shrinkage after the fact? And third, does a correlation exist between our water transmission test and theory and our experimental results? It's nice, but does it actually work? Answering the last question first, doing a correlation of our test results, we had 10 existing shrinkage ring samples that were cast for a previous project. We took those samples, we measured their crack widths visually, and then we also measured them using the water transmission setup. And we were able to get a pretty strong R-squared of 0.9, fitting with a polynomial trend, just based on previous research on water transmission test setups using Poisson's law, where you're measuring essentially through two parallel surfaces, a crack. We then tried to fit that data exactly to Poisson's law using the reduction factor of 0.6 that we've seen previously in research, and that was a little bit off. So we need to do a little bit more analysis, but we do have a correlation, but we don't have a strong correlation with theory yet, and that's something we're going to keep kicking on. After that, we then looked at the crack closure problem. Are these cracks just going to close after we remove them from the test setup? Because we did notice previously that when we left one on too long, a second crack would form, just because it's starting to re-tighten on itself. What we found is that when we stored our samples at high humidities, we were not seeing that crack closure, just because shrinkage had been abated. But when we stored them at ambient conditions, we were starting to see crack closure again. And this is more so just a testing procedure question. We can't test the samples, then leave them out for a day, and then test them again. We need to be very precise in our processes. After making these general questions solved, we were able to keep moving on with our work, and we started to actually look at our test results for our 3D printed samples. We fully completed 5 of our test samples so far, trying to complete more as we go. But we have 2 controls, 2 with a 2% self-healing agent and 1 with a 4% self-healing agent. First and foremost, with our shrinkage ring data, we looked at our time to crack, a relatively good measure in the ASTM for your risk of cracking. As you expect with a 3D printed concrete mix with a high amount of paste, there is a high risk of cracking, but we can also see that the inclusion of a self-healing agent is extending out that time to crack. This is pretty much a function of the inclusion of the self-healing agent, also including some sugar to allow the healing reaction to occur. What we're seeing is an extension, but not a meaningful one in reducing the risk of cracking ultimately. After that, we then looked at some secondary parameters, specifically the peak strain and the stress rate of our 3D printed mixtures in the restrained shrinkage ring test setup. Again, we saw high risk. Our stress rate was relatively high for all of these samples. Above 50 is generally considered high. As well as, again, we were starting to see a little bit leveling off where our 0 and 2%, or control and 2% self-healing agent were comparable, but our 4% was still decreased. After doing basic measurements for ring test results, we demold these samples and started to monitor their self-healing along the front surface. We took initial measurements from across our samples. Our control was at approximately 400 microns, with our 2 and 4% being at approximately 500 microns in size, so comparable. Didn't see any self-healing initially. Didn't see any self-healing through 7 days, got a little bit concerned. Didn't see any through 14, got very concerned. 21, very nervous. 28, didn't see anything. And I thought I was gonna have to redo this testing, and then I moved our samples, and I noticed, just gonna switch, all of our self-healing was visual on the bottom surface. Problematic because we didn't take pictures there, but it's something we'll do in the future. And it led us to one of our major conclusions that when you're monitoring self-healing, a very important aspect is the direction of water flow. So all of our samples were stored horizontal, or essentially flat on the ground, and as your water collected through, your precipitates were forming downward. Important to note, because in real world you may not see your self-healing, but you will see the effects of self-healing when you look at water transmission, as we will see on our next slide, which is our effect on the water transmission setup. So we have all of our samples here. We have our 4%, our 2%, and our controls relative to our expected trend line that we calculated with that 0.9 R squared value. We then backtracked out our effective crack widths by taking our measurement of water flow to the trend line, and we were able to calculate our decrease in perceived crack widths. For these samples, we saw that our control was essentially negligible, hovering slightly positive, but inside the range of error. Our 2% was a little bit more effective, and our 4% was even more effective than that. Just as you expect, increasing self-healing agent dosage will increase your effective healing, notably not completing self-healing entirely, though. From these results, we can take a couple of conclusions. First and foremost being that the inclusion of a self-healing agent in a 3D printing mixture will extend the time to cracking and decrease the peak strain. That the direction of moisture ingress will impact the direction of visible self-healing, impacting how you're actually perceiving your self-healing agent effectiveness. That optical methods for measuring self-healing are going to be limited and not always show the true effectiveness of the self-healing agents, and that the inclusion of self-healing agent can reduce the effective crack widths for water transmission of 3D printed samples. We're continuing to work to make sure we're actually seeing if there's a differentiation between our cast and our 3D printed samples. In our continued work, where we are completing additional replicates to improve our understanding of variability of these test methods, completing testing on our cast rings, as I just mentioned, as well as correlating existing fluid dynamic theory to water transmission results. If you have any questions, I'd be more than happy to answer them, and I want to thank the NSF IRIS project for allowing us to complete some of this work. Yep.